This is part 1 of astronomy and cosmology. In this topic, we will learn these 4 topics according to the syllabus. The first topic is understand the term luminosity. So luminosity is going to be the total power of any star or of any radiation star that is emitting some radiation. And that will be represented, since this is the total power, the unit of that will be represented in watts. And if you go back to O levels, we understand that power is equal to work done per unit time. So this becomes work done divided by time, which is going to be joules per second. So sometimes you will see this unit to be joules per second in the question. Sometimes it's going to be watts, but most likely it's going to be watts. So we understand what is luminosity. Okay, these are just 1 mark definitions. You just need to memorize them that way. The next idea is understanding what is a standard candle. Okay, so we've covered point number 1. We're going to point number 3 first. So standard candle is an astronomical object of known luminosity, because we need some standard value so that we can use it to compare it with the intensities and radiation and brightness of other stars. We need to have some base or ground value which we can use it to compare for others. So we have a standard luminosity, or you can say the standard candle for our universe, for our galaxy. The closest star that we have in observation is our own sun, and its luminosity is 3.83 power 26. You don't have to memorize this value. This is just given as an example. We will use this value to compare the brightness or the luminosity or the intensity coming from other stars. So for the sake of comparison versus distance and luminosity and power, we needed to know some standard value which we have found for the sun. In the incoming parts of the video, we will also learn how to find this value to begin with. Okay, so we understand what is point number 3 and what is the meaning of the standard candle. The last part is to use standard candle to determine the distance of the galaxy. This will be at the end of the video. First, we need to move towards some basics we are going to use throughout this chapter or throughout the other parts of this chapter. The first one is going to be the radiant flux intensity. This will be the next point. But before we get to that point, we need to understand what is 1 light year. The common misconception is that probably this is the time spent by light traveling for 1 year or something like this. But the true understanding of 1 light year is basically that this is actually a unit of distance. Previously, we had the unit of distance as kilometers, millimeters, centimeters. But when we're talking about objects at an astronomical scale, then this unit becomes too small for handling these values. So we had to make a new unit for distance calculation. So this idea actually stems from this concept that what if light was traveling for 1 complete year, how much distance would that have traveled? How much distance would light have traveled? So we simply use the formula speed equals to distance over time. The speed of light we understand is 3 into 10 raised to power 8 meters per second. This is distance, and if we give this a time of 1 year, which is going to be 365 days multiplied by 24 hours, multiplied by 60 minutes, multiplied by 60 seconds, this distance comes out as approximately 9.15 into 10 raised to power 22 approximately. You can calculate this on your own as well. So this comes out as 9.5 into 10 raised to power 15 meters. Okay, so again, no need to memorize this value, but it would be a good idea to keep this in mind when you're calculating distances based on astronomy. So when we are dealing with astronomical objects, for example, distance to the sun, distance to the other galaxies, we will be using the unit of light year, not meters or kilometers generally. Okay, so this is one new piece of information. Then we move on towards the idea of radiant flux intensity. This is basically watts per meter square. And what was watts? Watts were the power of the star, or the luminosity of the star, as we have discussed it over here, right? Then what is radiant flux intensity? This is just, simply put, this is just the radiation level or the intensity in 1 unit area or 1 meter square of area at a certain distance from the star. But if we want to use this concept, there are going to be some assumptions that we need to understand before we move on towards the formula. The assumptions are that the power of the star is uniformly radiated or is uniformly distributed throughout the surface area of the star. It's not going to be this way that, for example, if this is a star, certain part of the star is more active or is radiating more energy than the rest of the star, which is radiating, let's say, lesser energy as compared to this section of the star. So we're going to assume that the whole star is emitting constant or uniform radiation throughout space. And as you move away from the distance, or in terms of distance from the star, the radiation is spreading out again uniformly throughout the areas or surface areas encountered by those radiations. The second idea is negligible absorption through space when it is moving through space and when it reaches us. And when we observe it, we assume that there is no absorption in the medium or in the distance it traveled from the star up to our own eyes or detectors. Okay. Now, this formula suggests that if we know the standard luminosity or the luminosity of the star, if we divide it with the surface area of the star, which is of course the surface area, this surface area is derived from the area of the sphere, right? But how it actually comes to this point is not a part of the course. We're just going to use this formula to find out the radial flux intensity. Now, L, this is the luminosity, which is already known or will be given in the question, and D square or D is basically the distance from the star or the center of the star up to that point where you want to find this intensity. And of course, if you are closer to the star, your value of D will be smaller, and the radiation or you can say the intensity felt by you will be much higher than anything that is at a distance from that star. So this follows an inverse square law, which we can say that F or intensity or flux intensity is actually inversely proportional to D square, right? And of course, the unit is watts per meter square. Okay. Moving on towards a question using this formula to find out the distance of galaxy. This is the next part of the course, by the way. He says, understanding that standard candles can be used to determine the distance to other galaxies. Now let's use this formula, which is F equals to L divided by 4 pi D square, to find out the distance from Earth to that galaxy. Now, let's read the question. He says that we can ignore the names of the stars. It's not important. He says that Andromeda has, let's say, this watts per meter square. Now notice that this is the flux intensity, as the unit is watts per meter square. The luminosity of the star is this much. How much is the distance? Now we can very well see that this value, luminosity, is given over here, and the flux intensity is given over here. Now we just have to rearrange the formula, replace every value, and calculate the value of D. So D square, I'm not taking the under root right now, so D square is going to be equal to L divided by 4 pi F, and then of course D square will be taken over there for the under root. So L is given as 1 into 10 raised to power 30 divided by 4 pi, the value of F is 1.4. This is 1.4 into 10 raised to power minus 16. And then, of course, taking the D square, the under root over here is going to be this. When you calculate this answer, your answer is going to come out as 2.4 into 10 raised to power 22 meters. Okay. All right. So we understand the last part of the course as well. We understand point number 2 as well, how everything is going to be found out. Now let's go towards a few practice questions we have. This is from February-March 2023. So first part, he says, observing different stars from the Earth, give 2 reasons why some stars appear brighter than others. So one very common answer, based on common sense, is that they may be different. They may be at different distances from the Earth, right? So the first point will be different distances. The ones that are closer to us appear brighter. The ones that are far away from us appear less bright. And the second point would be that the brighter stars, or the stars which have less brightness, may be due to the fact that they have different luminosity. Different luminosity. Okay, you can go back to the question and memorize the marking scheme questions as well. Then he says, state what is meant by standard candle. As I've explained earlier, standard candle is an astronomical object of known luminosity, which we can use to compare for luminosity of the other objects or objects around it. Okay, you can also memorize the definition from this question. Then we move on to the next part. He says, luminosity is given The distance is given. He wants you to find the radiant. So the radiant flux density was F equals to L divided by 4 pi d squared. You can see that the questions are very straightforward, nothing too difficult. So this is 3.8 into 10 raised to power 31 divided by 4 pi, and d is being squared. So this is going to be 1.8 into 10 raised to power 24. Please don't forget to take the square over here. This value is going to be 9.33 into 10 raised to power minus 19 watts per meter square. And you can write this value over here up to two significant figures. Okay, I hope that we understand this topic.